In the previous lesson, we stopped looking at the different types of velocity versus time graph that we can have when you have an object undergoing some type of simple harmonic motion. As it suggests, it's a type of motion which means that you'll have velocity versus time graph, right, as the object is progressing. Now, there are two scenarios that we'll take this from, right? We'll take it from the standpoint when the object is starting from the equilibrium position, and we'll take it when the object is starting from the amplitude. Now, for this particular graph, we said that this one represents when the object is starting at the equilibrium position, right? At equilibrium position, we're essentially saying that the velocity, right, is going to be its maximum at the equilibrium position, right? Where if you want to find the maximum velocity, the maximum velocity is equal to omega times the amplitude, all right? That's how you generally find the maximum velocity for this type of system here, all right? Now, based on this equation, V naught would represent the maximum velocity. It's a cost graph, which means that it's going to begin right here, all right? There's another type of graph. I want to point out that you could also see the equation as to say V is equal to omega times A cos omega t, where omega right here, obviously you would know that omega is the angular frequency or the angular velocity times time, all right? So don't be confused if you're seeing these separate equations. If you see this one, it means the same thing. It's just that V naught represents the maximum velocity, all right? And similarly on this side, if you're seeing V naught again, it still represents the maximum velocity, where at maximum velocity, V naught is basically equal to omega times the amplitude. Now, for this particular graph, this is when the object is displaced from the amplitude, right? So if the object is displaced from the amplitude, you would use, this is the graph that would basically show you how the velocity is progressing over time. And of course, the minus sign in this equation just tells us the direction of the velocity, where we were able to summarize that using these graphs yesterday, or in previous lesson I should say, right? In the previous lesson. So this scenario is when the object starts from the display from zero, meaning from the equilibrium position, and we're essentially saying at that point your velocity is at maximum, right? I know it's not necessarily easy to understand when we say you start at zero and your maximum velocity is at zero, but if the system was to come back to the equilibrium position, right, what you would realize is that there will be a transfer of potential energy to kinetic energy, which just tells us that at this point when the object is going towards the equilibrium position, it's going to have maximum kinetic energy, which means that it's going to have maximum velocity, right? As it relates to acceleration, right, as we're looking here, we're seeing three different graphs. Now, if you remember the conditions necessary for simple harmonic motion, we could use this equation alone to explain the entire condition, meaning that acceleration for any simple harmonic motion is equal to minus omega squared times x, where x speaks to the displacement. By way of looking at this equation, it tells us that A is directly proportional to x, which just tells us that the more you displace the object from the equilibrium position, it's the more acceleration that you're going to have. Now the minus sign tells us that the acceleration is always going opposite to the displacement. Hence the reason why the acceleration for a sine displacement graph is, this is the reason why you find that the acceleration is within the negative region right here, right? So they are complete opposite of each other. They're opposite because this one here, it is going up like this. It's in the positive region, right? Now for the acceleration, the negative sign shows you that the acceleration is going in the opposite direction, right? But they are completely out of phase to each other. So this condition refers to them as being completely out of phase, which just shows that there's a flip, meaning that one is going positive, one is going negative. So the acceleration is negative in this case. Now, as you can imagine, that this function or this part of the equation of the equation here, this would basically tell you your maximum acceleration, right? And that is obviously at the amplitude. So for this particular acceleration graph, your maximum amplitude, which is your maximum acceleration, is going to be negative x naught, which is talking about the amplitude, right, times omega squared, right? So that is just what it is saying here, that at the amplitude, right, the acceleration is equal to negative x naught times omega squared, or you see them saying that a is equal to negative omega squared times a, where a just speaks to the amplitude. So that's what we are seeing here. This is for obviously when you have a sine displacement graph, which just tells us that um, the object is displaced from the equilibrium position. By way of comparing the acceleration graph and the displacement graph, what you're seeing here is that when the system is displaced to the maximum amplitude, that is when the system has its maximum acceleration. When the system comes back to zero, right, from the displacement graph, we're also seeing that the acceleration is at its lowest. All right. So those are some kind of key things that we can make reference to or point out whenever we're looking at and comparing the different types of graphs. As it relates to when the system starts at the amplitude, we're essentially saying that the velocity is at zero, right? So if you were to imagine your pendulum, so this is you holding on to the pendulum before you let it go. You're holding on to the pendulum. By holding on to the pendulum, you're not moving, which just tells you that the velocity is equal to zero at the maximum amplitude here. But the very moment you let it go, what you realize is that when the system reaches at the equilibrium position, that is when V is going to equal to max. All right, because as you can imagine, all of the energy stored in the system will be converted to kinetic energy. And at the exact bottom, that is when you would have the maximum speed. So it just shows us that, as a matter of fact, coming from this amplitude, you realize that the velocity is directing towards the center, or directing towards the equilibrium position. That's the reason why we have the minus sign, because it's going back towards the equilibrium position, right? So that's the reason why we have a minus sign here. And of course, you would, this is how you would draw your graph, saying that at the amplitude you have zero velocity, right? When the system is at equilibrium or passing through equilibrium, that's when you have your maximum velocity, right? And it continues. Now, as it relates to the acceleration graph, what the acceleration graph is showing us, it's showing us the complete opposite of what is happening to the displacement, because you can recall that acceleration is equal to minus omega squared times x. So whatsoever is happening to the displacement, the same thing is happening to the acceleration, right? But it's just happening in a complete opposite of each other, right? Which is just the minus sign just shows us that it's the opposite of what is happening, meaning that, you know, it occurs within the negative region. So if your displacement is in the positive region, starting from the amplitude, then you would expect that your acceleration, which is just telling us that it is going towards the center. So similarly, if you were to draw the pendulum system, right? At first, you would have displaced the thing to some distance along the x-axis, right? Now, as soon as you let go this the system here, you would expect that there will be an acceleration going towards the center, directing you towards the center, right? As you come to the center, what you realize is that your acceleration goes to zero, right? Your acceleration goes to zero because of the fact that the acceleration is directly proportional to the displacement. So the further away you displace the object, it's the more acceleration that it's going to have at the amplitude. So from this, when the object is at equilibrium position, we're also seeing that the acceleration is at zero because of the fact that acceleration is equal to minus omega squared times x. If there's no displacement, as you can imagine, then there will not be any acceleration. So once there is some type of displacement, then you record some acceleration. When the object has moved and go to the second amplitude, then that is when you can record your maximum acceleration, right? So you can imagine that the object is moving from the equilibrium position, back to this position here where you record the next amplitude. At this location, you would expect that is when you would have your maximum acceleration taking place. And of course, this acceleration is going to be directed towards the center, right? Whereas the displacement is going in the opposite direction. So that is just what it is saying there. And obviously, if the object is starting here, then you can clearly see that it's going to be a cost graph, right? It's going to be a cost graph. So acceleration is equal to minus x naught omega square cos of omega t, right? So that completes this acceleration graph. We must be able to can look at these graphs and understand. It's best when we start off with your displacement graph, and then we analyze our way into the velocity scenario, then obviously into the acceleration scenario. So we must know which graph will come into play depending on where the object is displaced from, right? There are other graphs, or there are other things that we need to talk about, right? Such as when we can say the velocity as a function of displacement. So at first, we looked at the velocity versus time graph, right? Now we're going to look at velocity versus displacement. This is just showing us the variation in the velocity and as it will parallel to the displacement. All right. So let's think about it. When you are at the zero mark, or you're at the equilibrium position. Previously, we said that that is when you would have your maximum velocity, right? So when the object is at zero, or at the equilibrium position, you would expect to record your maximum velocity. When the object is at the amplitude, as we would have pointed out already, that is when you would have zero velocity, right? And it continues. So this graph here is essentially showing us what is happening as we consider the displacement, right, versus, or the velocity versus displacement. Mind you that there is an equation related to this that says v squared is equal to omega squared times a squared minus x squared. Now, if you are at zero displacement, where x is 0, it means, so at x equals 0, you're going to realize that v squared is equal to omega squared times a squared. This is essentially showing us that at zero displacement, you record your maximum velocity. All right, maximum velocity. Now, what if x is equal to a? So at x, if x is equal to your amplitude, that is when you will not have any velocity. And by way of the equation, v squared is going to equal to omega squared times a squared minus a squared. A squared minus a squared gives you 0. 0 times omega squared, v squared is going to equal to 0, which we are seeing right here from this particular equation. This equation was derived from this concept here, right? It's not an easy concept to understand how they derived it, but I'm going to walk you through it. Hopefully you will get it. But you must remember this equation as well, to say that v squared is equal to omega squared times a squared minus x squared. All right, we're going to look at that a little. Now, here we have an object that has been displaced from the equilibrium position, right? It has been displaced from the equilibrium position. The object is now located at this position. It's located here. Now, as you can imagine, if the object is moving all like it's in a circle, you would expect that the velocity, the maximum velocity, is going to be a vector quantity that is tangential to the position of the object, right? Or the tangential to the curve or the path that the object is moving in. So if the object was located here, you would expect that the velocity would be directed as such, right? But we're considering when it's here. So this will be your maximum velocity, right? That's your maximum velocity. Now, what we're concerned about the x component of v naught. As you can imagine that if the displacement is along the horizontal, we want to know the velocity that is along the horizontal, right? So we're going to resolve the component of v naught, which is the velocity that the object has, right? As you would have seen me highlighting it a while ago, that right here is that velocity. Now we're going to split that velocity into its horizontal and vertical component. But there are certain things that we must remember. There's an angle right here, which we refer to that as theta, the angular displacement. So this angular displacement is reflected on the outside here, right? So the same angle in between right here is the same angle that will be reflecting right here as well. Now, by splitting v naught into its y component and x component, this is what you would essentially be seeing, that vy is going up like that. That's the vertical component. V of x is going towards this side. Now, by way of considering z angles, the angle interior right here is also equal to this angle right here in between here. So whatsoever theta is on this position, all right between the x-axis and the displacement or the distance away from the origin or from the central point, right? You would essentially see that we're having a z angle being formed right here. So the angle, right, between r, which is your radius, right, and the horizontal component of the velocity, that is also equal to theta. So as we can imagine, by using the whole concept, but before we even go into that, let's leave this as such. But one other thing we want to realize here is that we have a triangle being formed out right here. We have a triangle being formed out. Now, MB, based on, this is the side of MB. MB is going to be equal to, since we're dealing with a right angle triangle, that side is going to be the opposite to the triangle. So essentially, if that side is the opposite, it means that sine theta is equal to MB divided by the hypotenuse, where OM is the hypotenuse, right? OM is the hypotenuse, which is the radius. So essentially, you could go ahead and say, all right, MB divided by OM is equal to sine theta. Having said that information, we can then realize that we can solve, or we could transpose for MB. As you can see right here, MB is equal to OM sine theta. But we said that OM is R, which is the radius, right, of the circle. No, but what does R represent? By using Pythagoras theorem, right, we know that Pythagoras theorem says a squared plus b squared is equal to c squared, but in this case, c is equal to r. So rather than writing c, we just write r, or we can even rewrite that a little bit here. Let's kind of rewrite that in a more refined form using information that we know from this. Mind you, MB is the amplitude, because that is the distance away from the equilibrium position. That is m. That is the amplitude. All right. That's MB. This side is R. This side is X. This side, as we said, is A, the amplitude. So Pythagoras theorem would have told us that R squared is equal to X squared plus A squared, right? But we want A squared, or we want A to become the subject, which is MB. We want that to become the subject. By making that become the subject, we realize that A squared is equal to R squared minus, well, not that, 1 second. Yes, indeed, it's correct, yeah. Yeah, so R squared minus X squared. So that's what A squared is equal to, which is the same thing as MB. So MB is the amplitude. So if you're looking at right here, you see that MB is equal to the square root of R squared minus X squared. This is us just deriving this equation here. That's what we're essentially doing. Okay. So we have come to a point where we did say that MB, which is the amplitude, is equal to R sine theta. So by comparing these two things or equating them, we're saying that R sine theta is equal to the square root of R squared minus X squared. Okay. Now, as it relates to the velocity that we're talking about, which is the X component, right? That velocity is this thing right here, right? So after resolving V naught into its horizontal and vertical component, we would have gotten Vx. So Vx is going to be equal to V naught sine theta. But remember, V naught, this is minus by the way because it's going towards the center. Remember, V naught is equal to omega times R, or we could say times X. Not times X, but times A rather, right? Times A. Okay, so we could go ahead and rewrite this to say Vx is equal to minus omega A times sine theta. But I think it's best if we leave it as saying V of X. I think it's better if we say V of X is equal to, let me show you what I mean. V of X is equal to minus omega times R sine theta, because what you're going to realize is that there's going to be a substitution, because we did say that R times sine theta is equal to the square root of R squared minus X squared. So by us getting this equation here, we're going to substitute for R sine theta. We're going to substitute for R sine theta. When we do that substitution, we have this to say that V is equal to minus omega times the square root of R squared minus X squared. Good. So with this now, this essentially depicts the velocity, right? The velocity of the system. But now it says to us that, but since R is equal to A, which is the amplitude, rather than writing R, we could write A, which is the amplitude. So V is equal to minus omega squared times the square root of A minus X. Well, yeah, A squared minus X squared. So this right here is basically showing us an equation that is linked to the displacement and the velocity, all right, which we can look right here. So if you were to represent this equation on a graph, this is essentially what you would be getting, which is just showing us that at such strategic location, when the thing is at 0, you would expect, if X is at 0, then that is when V is going to equal to omega times A, right? That is when you would have your maximum velocity from being displaced at 0. right? So this is how we get the whole concept to say that v at the maximum, or at zero, I should say, at zero velocity or zero displacement, my bad, at zero displacement, v is equal to omega times a, which is the maximum velocity of the system. So it says that this equation tells us the velocity v is at maximum as a particle passes through the center of the simple harmonic motion. I know this proof might be a little bit complicated or a little bit hard to do, but it's just kind of applying all of the whole, using Pythagoras theorem, using trig ratios a little bit here, that kind of thing, to come up with this entire thing, right? But note this equation here, or this graph, I should say, right? This is just talking about the velocity versus displacement, right? Now we move on to talk about the acceleration as a function. We did talk about acceleration already from the graph, right? But one of the things I want you to realize is that when you're displacing the object from equilibrium position, right? When you're displacing the object from equilibrium position and it reaches its amplitude, once it reaches the amplitude, you realize that the acceleration is directing towards the center, which is right here, right? When the object reaches over on the other side, you will observe that the acceleration is going in the same, or it's going towards the center, right? The velocity as well kind of shows what is happening. So when you reach at maximum, velocity goes to zero, then it directs back towards the center, right? And as you can see, when the object is passing through the center, the velocity is at its largest, meaning that the arrow is at the largest amount, but when it reaches over here, it decreases, all right? For the acceleration as well, as you can see, the size of the arrow matters. When the object reaches on this side, the acceleration is at its highest, which just tells us that acceleration is directly proportional to displacement. This right here just kind of showing you how we got the proof and all of that, right? In terms of getting that particular cost equation for when the object is displaced from the amplitude, all right? So at all times, the acceleration is going to be inversely proportional to the displacement, and there will always be a negative sign right here, right? So A is equal to negative omega squared times A, where A is the amplitude, cos omega t. This just tells us that the system is starting at this location, which just tells us that the displacement is from the amplitude, all right? So it is by comparing the displacement and the acceleration time graph, you can clearly see the definition, the defining characteristics of simple harmonic motion. It says that acceleration is directly proportional and in the opposite direction to the displacement. It says in simple harmonic motion, acceleration and displacement are completely out of phase to each other, right? As I would have highlighted already, they say that they're out of phase, which means that one is in this negative region. So this is the acceleration. Then now for the displacement is completely out of phase. So this is kind of like the progression. So this is the displacement, and then now this is the acceleration. Good. Where the acceleration starts, it's in the negative portion. That is the reason why you have this negative sign here, to say that at all times they are going in opposite direction to each other, but they're completely out of phase. By being completely out of phase, it means that they're a reflection of each other. They are basically reflections of each other, So this is just to sum up what we have been talking about. Right? We can put everything into context now. Similarly, we can also have an acceleration versus displacement type of graph, right? What this shows us is that when the object has no displacement, if the displacement is equal to 0, then the acceleration is equal to 0. So if you have not displaced the object from the equilibrium position, then it therefore means to us that the object will not have an acceleration. But the very moment you displace the object, right, you displace the object, then what you're going to realize is that it's now going to have a velocity. Well, not a velocity, but it's now going to have an acceleration. But the maximum acceleration is when the object is now at the amplitude. So let's look back at this. So that's our pendulum. This pendulum is starting at equilibrium. Well, not at equilibrium, it's starting at the amplitude. If you're starting at the amplitude, that is when you're saying that you have maximum acceleration. You're saying that you have maximum acceleration at this location when your amplitude is equal to a, right? Yes. Similarly, as the object passes through the central point and goes over to the next side, right? You would expect that when you're at this position, that's when you would record um, maximum acceleration, right? So that's pretty much what we need to know in relation to the graphs. We need to sit down and kind of look at them and study them a little to just understand what is happening at each point. And I don't think it's that difficult to do. Okay. All right. Before we talk about the spring, we just want to kind of tie things together a little bit. We have been seeing the different types of equations and so forth, right? And we just want to kind of just become a little bit more familiar with how these equations really make sense to us. So this is like a general question, that you can see from time to time. It says that the displacement of x at time t of a particle moving in simple harmonic motion is given by x is equal to 0.25 cos omega, well, cos 7.5 t, where x is in meters and t is in seconds. It says use the equation to find the amplitude, frequency, and period for this motion. So by looking at this equation, that's the equation that they're talking about. So the equation gives us that x is equal to 0.25 cos 7.5 t. Now, obviously, this reflects the equation that says x is equal to a cos omega t. By just comparing the things here, a is going to equal to 0.25 meters. By comparing this, you know that omega is equal to 7.5 rads per second. The unit for omega is rads per second. Cool. So this is what we have so far. This information here is the amplitude. So we have that information. We know the angular velocity, right? The question wants the frequency. So recall that omega is equal to 2 pi divided by t, or omega is equal to 2 pi radians times f. All right? So we could literally compare, or not compare, but transpose omega equation. Omega is equal to 2 pi f. We want to find f. Now, there's a difference between angular frequency and frequency. Right? So angular frequency is talking about the speed. Frequency just speaks to the number of oscillations per unit in a given time, passing through a given time. Or we can say that frequency, yeah, basically the number of oscillations within 1 second. Basically, that's what frequency talk about. So we could transpose the equation to make f become the subject. So f is going to equal to 2 pi, well, not 2 pi, but omega divided by 2 pi. Omega divided by 2 pi. You found out what omega was. Omega was 7.5 from the equation, divided by 2 pi, right? We should be getting some information to say that the frequency is equal to 0.83 per second, or you could say 0.83 hertz. But I would recommend using, per seconds in this case. It's the same thing. So that can be used. So we have that. It also says find the period. You should remember that period t is equal to 1 upon f. Having that information, having the frequency information, so 1 divided by 0.83, that's going to give us a value to say that the period, let me just confirm here, give me a second. Let me just confirm. I think it's the other way around. So the frequency is going to be equal to frequency is going to equal to 1.19. So 1 divided by 1.19 gives us a time period of 0.83. So that's what you guys should be getting. Well, no, I still kind of wrote it a little bit wrong. Yes, I think it's correct now. Yeah, this should not be hertz though. This should be seconds. All right. The question then goes to tell us that find the displacement when t is equal to 0.5. So let me just clear this information. So t is equal to 0.5. So it means that we want to find x. X is equal to 0.25 cos of 7.5 rads per second times 0.5 seconds. Okay. Now, as you can see, seconds and per second cancels out, leaving us with an information to say 0.25 cost of 7.5 rads times 0.5. Now, this becomes particularly important whenever we are given a scenario as such and we're trying to find cost of some number that is radian, that is in radians. We have to make a conversion as it pertains to radians. There's something that we must understand. When you complete an entire circle, right? So you're starting at this location, you travel all the way around the circle and come back here. We would have essentially said that you have completed 2 pi radians, all right? So that just speaks to you completing the entire circle. Where we're also saying that once you complete the entire circle, it means that 2 pi radians is equal to 360 degrees. So radians is like another way of representing angles, right? So it's the same thing it means. What if I want to know what radians is equal to? I can make radians become the subject. So radians, or we could say rad, is equal to 360 divided by 2 pi, which is saying that 1 rad is equal to 180 divided by pi. That's what 1 rad is. So in this case, because we're trying to find cost of 7.5 radians times 0.5, I have to convert rads back to degrees. I have to convert rads back to degrees. So we're saying that cost of 7.5, where if I see rads, I'm going to write 180 divided by pi, right? And obviously it's still being multiplied by 0.5. Okay, so we go ahead and say cost of 0.25 or x of 0.25 is equal to cost of, let's work it in the calculator. So 7.5 times 180 times 0.5, that gives me a value of 675 divided by pi. 675 divided by pi, cost of, not cost, x of 0.25, cost of 214.8. So let's find cost of 214.8. When we do that, we're getting to say that x is equal to 0.25 times negative 0.82. Negative 0.82 times 0.25. We get that the displacement is going to be equal to negative 0.1 meters. Right? So that is your displacement when you are at 5 seconds. So in essence, this is what the graph looks like. When we're using a cost graph, it means therefore that the graph starts at the top of the system. Let's kind of put a little bit of information on the graph. You know that this is going to be the displacement side, the x side. I mean, x is on this side, t is on this side. Now it tells us that to complete one period, the time is going to equal to 0.83. So we could be going up by, let's call it 0.4 0.8, 1.2, right? The amplitude is 0.25, so that's where we're starting. So this is kind of like this side is going to be negative 0.25. Give me a second here. This is not the perfect kind of graph. Oh, I made a mistake and delete everything. But we don't need to necessarily draw the graph, but the idea is that you would have a graph looking like this, coming all the way down, coming all the way back up, right? When the graph reaches back at this location where it started, then that would be one period, which would be equivalent to 0.83, right? That would record one period. So from amplitude to amplitude, that's one period. Right? That's what I wanted to show you a while ago. Right? From amplitude to amplitude, that's going to be one period. Okay, so that completes that. Now, take this question. It says a mass oscillates. Well, you would not be able to can do this. You will not be able to can do that one. Right? So we'll pick up in another lesson where we talk about the period of a simple pendulum. All right?